Good morning. So I'm Jérôme Kiefer and I will present you a short tutorial on how to perform the calibration of a diffraction image using the Jupyter notebook. So I'll show you my screen. So the Jupyter notebook looks like this. So usually you access it via a web browser. Here it's Firefox running. And you have some URL and you end up with a page like this, and you can ask for a new notebook. So what is a notebook? A notebook is an ensemble of cells where you can perform some calculations. For example, we can do 6 times 7 and it gives us the answer. Well, the idea of this notebook is that you can execute some Python code or other programming languages. For example, I can print hello, and by pressing Shift Enter, it will evaluate this. So the idea of this tutorial is how to perform the calibration of a diffraction dataset. And have the position of the detector compared to the beam and to the sample position. So for this, we will need to integrate some images into the notebook. For this, we will have to use an extension of matplotlib like this. So type %matplotlib, for example, nb8gg. If you're using the standard Jupyter notebook like I'm doing, or if you're using already Jupyter Lab, you can do %matplotlib widget. So this will activate the integration of matplotlib into the browser. So first of all, we'll load some images. So we'll start with pyFAI has a set of test images that we will use. And the image will load. Get image is a, so this is a fairly standard image. So if we want to look, so EMG is just the path for the file. So we have to use Fabio. And image contains now the array with the data. So pyFAI has some tools in order to display the image. For example, setting the curves in log scale, the levels of colors. So from pyFAI.gui import Jupyter, and then Jupyter.display of the image. And here we have the plot of the image that we can move around. We can zoom in like this, and we have the values, the coordinate of the cursor with the relative intensity, while the intensity here is in log scale. Okay, so the idea of this tutorial is to take this image, and we see here different rings. We see 5 rings, and the position of those rings define basically the position of the detector compared to the sample. So if we know that the sample is silver bayonet and the wavelength is at 1 angstrom wavelength, and we know the characteristic of the detector, we should be able to determine where the detector is in space. And for this, so we'll first define the wavelength. So it's 1 angstrom, or 10 to the power minus 10 meter, because pyFAI runs in with the international system in internal. Now we'll okay. Then we have to define the detector. Some import pyFAI, and let's say Pilatus is pyFAI dot detector factory of Pilatus 1M. So here we have the detector, which is already calibrated with the gaps already at the right place, and the pixel size, which is correct. In addition, we need to know that the calibrant used, the reference sample, is a silver bayonet. So we define, so we have to import from pyFAI dot calibrant. So silver bayonet. So we have to first set the wavelengths used. So okay, so we have a calibrant with 49 reflection at the given wavelengths. And with this, we can start to perform the calibration. So to perform the calibration, we have to import a new module. So from pyFAI dot GUI dot Jupyter, sorry, dot calib import calibration, and so the calib object is simply calibration with the image that is provided. So we need to say that the calibrant is silver bayonet, that the wavelength is the wavelengths we have, and that the detector is our Pilatus. So this opens us a new plot, and this plot that we can resize. We have here, well, basically the same image. We have the color bar that gives a relationship between the intensity of the pixel and the color and the intensity. So here we have the actual pixel intensity, so -1 for the gaps, and yeah, some intensity. We have the beam stop, and here we have two additional widgets. So refine is the one that we will use at the end to actually perform the calibration, and ring has to be set to a different value when selecting a ring. So to select a ring, we just put the mouse on one of the ring and perform a right click like this. So this has highlighted one section of the image, as we can see here, and picked some control point within this region. And it created the group A, which correspond to the group of innermost ring. So we switch to the ring number 1. So this is 0 based, like most of the time in Python. And this is different from pyFAI calib 2 that maybe you are used to play with. So we perform the same. We change the ring number and we click on the second ring, and we'll do it a third time on the ring number 3, where we will pick, for example, some points here. With this, basically, we have 3 groups of points, which should be sufficient to provide us with the beam center and the detector distance, and we just have to click on refine. So the refinement has started. Okay. a bit of time. And if we go back on the image, we see that there are some graphical bugs, sorry for this, that the tool overlaid in dashed color the expected position of the ring. So we see that we have a fairly good calibration, and we have been able to determine the sample detector position around 1.6 meter away from the sample. So what can we do with this? So the first thing to do maybe is to retrieve the geometry refinement object. So let's call it GR as geometry refinement. And inside calib we have a georef object. And we can, for example, print GR, so that will print the geometry refinement. But we can also print the parameters that were used to perform the calibration. So some parameters have been kept fixed, and also the cost function that we got at the end. So that's gr dot K2. So here we see the latest, well, the optimized geometry. So we have the position of the beam center. We have the tilt, which is 4 degrees. It's quite a lot when we consider that it's a Sachs geometry. We have performed the calibration by keeping the wavelengths and the rotation 3 to 0, and we got a cost function which is 1.6 10 to the power minus 7. With this, for example, if we consider that the tilt is pretty high, we may want to set the tilt to 0. So this can be done with gr dot rot1 equal gr. So like this, we say we set all rotation to 0, and we can perform a different another refinement. Refine 3, fix, and we provide the list of parameters that we want to fix. So it's rot1, rot2, and rot3, and to also the wavelengths. Okay, so we have some refinement, and we can again calculate the, and we see, oh, the refinement is even better. And if we want the geometry, we can just ask for gr, and we have the distance. It hardly moved compared to previously. The beam center moved by half a pixel, let's say, and here the tilts are all set to 0. So now, if we want to save this configuration, for example, we can do gr dot save of Jupyter calib.pony. So that's a way to do it. And another way to do it is we can get the config, and this will simply print the content of the pony file. So we have the detector definition, we have the distance, so pony 1, pony 2, which correspond to the beam center x and y, and the 3 rotation and the wavelength. So this is enough to define the geometry of the detector. Now, if we want to perform some azimuthal integration, it's advised to extract those information from the geometry refinement object and create an azimuthal integrator. And this is simply done by pyFAI.load of GR, and so AI now looks the same, except that it has lost all the capability of fitting the geometry. So it's a tool to perform the Azimuth integration. So now we will perform the Azimuth integration. So in 1D, we can do AI dot integrate 1D of the image. Let's say we take 1000 points, and let's do the same. We'd perform a 2D integration and just print you res1, which contains the array in x, y, so in Q unit and in intensity. So this is the default setting, but you may want to plot this. So what we can do is use matplotlib. So we'll import subplots. So we create some subplots like this, and then we'll populate them. Sorry, Jupyter dot plot 1D. So res1 is the 1D integration. AX0 is the first axis of the plot, like this. So it could be interesting. So we've seen that it retrieved in addition the scattering vector, which was stored into this res object, the intensity, the title of the graph. This is all done automatically. And we can provide in addition a calibrant, which is, and we have overlaid the position of the expected rings. The same can be done with the second. So we perform a plot 2D. S2, that's the second. Okay. Oh, we are missing just the title. So like this, we have the plot with the overlaid position of the expected rings. We see that it matches pretty well. We can zoom like this. We see the position of the gaps. And with this button, we can save directly the image within the browser, and this is an image which is of pretty good quality and that can be included in any report. Okay, with this, I hope that I've proven you that it's possible to perform the calibration. The Jupyter notebook has been in development for 10 years, and it's a very appealing tool when it comes to perform remote data analysis. So the idea is that the ESRF user can log in into the service, which is called Jupyter Slurm. So like this. And they can directly choose the kind of computer they want to have. So currently there's very little resources available, and they just click here to have one Jupyter server that is running for them, and which provides them with an interface like this, and they have a direct, fast access to all their data. with this, I'd like to thank you for your attention, and if ever you find some bugs, please report them into the pyFAI issue tracker. So just go to github.com, select Skit, and you'll find pyFAI. And simply click on issue and new issue and report here the bugs that you have seen. So this interface is fairly new, and we hope to improve it in the coming future, helped by the issue that you will provide us. Thanks for your attention. Bye.